In other videos, we discuss using a t-test to determine whether a regression coefficient is statistically significant. Now, technically, what we mean by that is whether it's significantly different from zero that we can reject the null hypothesis that the coefficient is zero. It is nothing. But there are times that we may want to compare a regression coefficient to some other non-zero value. Here's how you do that. First, let's step back and review how the t-test for a regression coefficient works. Here's the coefficients table from an analysis in which we use school quality and study hours as predictors of student grades. Let's focus on the effect for school quality. Remember, t is calculated by dividing the unstandardized regression coefficient by the standard error of the regression coefficient. So using this example, if we look at school quality, the unstandardized regression coefficient was 0.066, and the standard error for that regression coefficient was 0.017. If we divide 0.066 by 0.017, we get 3.821. The results, what we would expect to see for that in the coefficients table within rounding, right? Now, technically, that oversimplifies things a bit. Think back to a one-sample t-test. In it, we compare our sample mean to the mean that we expect to see if the null hypothesis is true. It's actually the same thing here. This really is just a one-sample t-test using a regression coefficient b instead of a mean. If we write the formula more generically, and you may see it written this way sometimes, it's actually b, our observed b, minus b null, that value we expect to see for that regression coefficient if the null hypothesis is true, divided by the standard error for the regression coefficient. Now think about it. What's b null? Well, in nearly all cases, it's the value for b that we expect to see if there's no effect. And in regression, b, that slope, has no effect when b is equal to 0. So do you see where I'm going with this? Therefore, in nearly all cases, our t formula for a regression coefficient simplifies to b minus 0 divided by the standard error of the regression coefficient. That's just b divided by the standard error of the regression coefficient. So that's why you typically see this formula just written as b divided by the standard error. It's the same as saying we're testing whether our coefficient is different from 0. But this is where it gets kind of cool and handy. B null doesn't have to be 0. It can be any value that we expect to see if the null hypothesis is true. In other words, it can be any value to which we want to compare our regression coefficient. For example, let's say that you're testing a literacy program that goes for half a year, and B indicates how much student reading scores increased in grade levels following participation in the program. At the end, the default t-test for your regression coefficient will examine whether the gain is not 0. But it's half a year later. There should be some gain even if the program doesn't work. So you may not care if it's different from 0. Instead of comparing b to 0, you may want to compare it to 0.5, half of a year, and test whether the reading gains were more than one would have expected during that half of a year that the program ran. The default t-test in multiple regression doesn't do that. You need to run a new t-test with your own b null in the numerator. Now, it's straightforward and the right thing to do if you want to compare b to some specific known value. So that's what you do if you, again, want to compare your B to a specific known value. But what if you want to compare your regression coefficient to the value of a regression coefficient that someone else obtained in a different study using a different sample? That's a little trickier because their value for their regression coefficient is an estimate of the true value for that population. Now, it may look exact and precise, but it's a little squishy because it's an estimate. If we want to know whether our B is different from their B, the value of their regression coefficient from their study, we have to take into consideration that we're not 100% certain what the value of their regression coefficient really is because it's going to vary sample to sample to sample. The formula for doing this is Z equals B1, that's our regression coefficient, minus B2, that's the regression coefficient for the other study, divided by the square root of the standard error of B1 squared plus the standard error of B2 squared. Now remember, the standard error of a regression coefficient, that's that S sub B, is the amount of variability we expect to see in our estimates of a regression coefficient from sample to sample. That's why we use it as our yardstick in our t-test for regression coefficients. But in this case, we're talking about comparing estimates for two regression coefficients from two different samples, each with their own standard error. So we need to factor in both standard errors into our equation. To do that, we square each standard error, then add them up and take the square root of that sum. This gives us the standard error for the difference in our regression coefficients. Now, if you pause for a moment and think back to intro stats, you may notice that this is very similar to the standard error of the difference between means in the two independent sample t-test. We're just using standard errors for regression coefficients instead of standard errors for means. Pretty cool, isn't it? And notice that we're squaring the standard errors, but then taking the square root of them to put it back on that same general scale that we use when we are using standard errors as our yardstick, right? So, again, that's pretty cool. Therefore, the formula for comparing two regression coefficients from two different samples is Z equals B1, the unstandardized regression coefficient from the first sample, minus B2, the unstandardized regression coefficient from the second sample, divided by the square root of the whole thing of the standard error for the first regression coefficient squared plus the standard error for the second regression coefficient squared. Now remember, we're not comparing two regression coefficients in the same analysis. We're comparing two regression coefficients for the same variable from different analyses with different samples. And because of this, there's a few things we have to keep in mind if we want to do this. First, when I say the same variable, I mean it's the same variable. It can't be a different variable measuring the same construct. You can't compare the regression coefficient associated with the Beck depression inventory in sample 1 with the regression coefficient associated with the Mason mood index in sample 2. Similarly, it has to be on the same scaling. You can't compare the regression coefficient for income based on dollars in sample 1 with the regression coefficient for income based on euros in sample 2, right? Kind of obvious. And it has to be this same multiple regression equation. Both of those regression models in both studies have to use the same set of predictor variables. Otherwise, as we'll see over and over and over again, the value of the regression coefficients will change based on the other variables that are included or excluded from a model. Now, how common is this? Again, remember the models need to be exactly the same. Consequently, you'll regularly see people compare their regression coefficient to some specific non-zero value, but you're much less likely to see someone compare their regression coefficient to a regression coefficient in a different study with a different sample. Well, at least you're less likely to see it done appropriately. But it's good to see that it's possible and to understand what's required for you to try that. Okay? Take care. Bye-bye.